dType version 2.0 is functional, based on a pipeline-like graph interpreter built with UL+, which can be compiled to WebAssembly or the EVM. Tailor is the set of tools which brings dType at the fingertips of programmers. The Tailor on-chain graph interpreter is used for building type definitions. Type definitions are essentially functions in the form of graphs similar to pipeline graphs, created on top of a recursive apply engine and a set of native functions. The encoding format that you will see in the examples is a typed format, where values always come with their type. And this will act as an intermediate representation between other types of encoding and decoding. If you want to know more, watch the dType version 2.0 presentation linked in the description. Today you will see examples of casting a type to another, integers, unsigned integers, and arrays. I already registered the graph-based definition for the uint and array types, along with a casting algorithm for arrays. Let us start from an unsigned integer. The type signature is this, 4 bytes, where 11 is specific to the unsigned integer type and 4 is the size in bytes. This is equivalent to the uint 32 from Solidity. So we just called the new function for this type, and this is the result. All inputs and outputs are wrapped in a tuple, which starts with EE. This tuple has a size of 1, which means it contains one element. Next we have the additive lengths of the tuple elements, in this case a size of 8 bytes, and then the actual element, which is a typed value. On the first 4 bytes we have the type and then the 0 initialized value. This is our 32-bit unsigned integer. Now we will take this type with a value of 8 and cast it to a 256-bit signed integer. We start with the signature for the execute function, which is the main entry point in our program, and then the signature for the cast function. Next come the inputs wrapped in a tuple, and we will have 2 arguments. The first one is the type we are casting to, so int 256, which is 12 is corresponding to the signed integer type and 20 is the size in bytes, which is 32. But this is the value. The type of this value is byte. And this is our first argument, which has a size of 8 bytes. And this is our second argument. This works because we are casting from a smaller range to a bigger range, and we can see the actual returned value is this one, wrapped in a tuple with one element of length 36 bytes. So the type has changed. It's now a signed integer of 256 bits, and the actual value is this, which has been left padded. If the value's actual size allows, we can also downcast. So we can take this value and downcast it to an unsigned integer of 8 bits. We again start by adding the proper signatures for our operation, the type that we are casting to, and bytes for the type of this value. And this is our result. A uint 8 and this is the actual value. Now, if we try to cast a negative value to an unsigned integer, we get an error, and this is our negative value of type int 32. We get an error. But we can cast a lower range signed integer to a higher range signed integer. And this is our new value of size 16 bits. And we can also cast arrays. I have already stored a graph that does exactly this, and can take an array of any length and of any element type. So we are going to call the same execute function, and this is the signature for our casting graph, and then a tuple of 2 elements, where the first one starts here. So we want to cast to an array, which starts with 4, of size 3, which contains unsigned integers of size 8, from an array of size 3, which contains signed integers of size 4, and the values are 2, 5, and 4. And this is our result. A tuple of 1 element, which is this one, and we see it's an array of size 3 containing unsigned integers of size 8, and the values are left padded to reach 64 bits, 2, 5, and 4. Solidity, for example, does not have tools for casting arrays, but this will be possible with Taylor.